That's fine. Yeah. I always say I'm not awake at that time to check anyway.
No.
Yeah, so like an hour or two is past then.
Yeah, I was aware. I really I said, oh, Cal 3, it's no big deal. And then I started doing it. I'm like, wow, wow.
It catches by surprise.
Yeah.
It looks simple. It's a rectangle, but then when you have to do four sides, it takes a while for sure.
Well, it wasn't that one, just that one. It was also the hyperbola.
Oh yeah. That one is tricky too.
Yeah.
Yeah.
Oh, it wasn't too bad. But for the exam, that's not. If I miss surgery lecture, if we sit during the exam, we're not going to focus too much on the line and goal during.
Exactly. Yeah. So for the exam, so for the homework guide, you do both. But for the exam, you can choose whichever one you do. But generally, the double window is easier to do. Yeah. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Last week before spring break, so hopefully we can get through this week and we can all relax for a week after this. Okay, all right. So plan for today is we're going to continue our lecture notes on Fourier series. So we kind of just introduced that concept last week, or we didn't even introduce it. We kind of just talked about just periodic functions in general. So we're going to expand on that today. We'll kind of go into what the Fourier series expansion shows, and then do a bit of computations there. Okay. One announcement. So homework 5 has been posted onto the Canvas site. So homework 5 has to do with Fourier. So I am assigning it now, and it's not due till after spring break, but my hope is that you'll be able to work on it this week, of course. But I set the due date to be not the week immediately when we come back, but the Sunday after that week we come back, so that realistically, you can complete the homework by working on it this week and just the week that we come back. And so I know it's not the cleanest to have an assignment that kind of bleeds over into spring break, but I did hopefully kind of leave some leeway so that you don't feel like you have to work on it over spring break. Because I think spring break should kind of be a break for everyone. It's just that with the timing of the topic in this class, I did have to assign it this week. But just know that there is time after spring break for you to do. Okay. So I believe I set the due date to be the Friday or the Sunday after spring break. So you have time to do that. Okay. Okay. One more announcement. So I did bring the exams today as well, midterm ones. And so if you didn't get a chance to pick it up, today will be the last day that I bring it. I said that last week, but then I got a few requests to bring it today as well. So today will be the last day. So if you haven't picked up your exam after date, you have to come to my office to pick it up. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and resume our discussion from last week. Okay, so last week we kind of ended our lectures talking about the concept of sound, right? And in particular, sound has, I would say kind of two main characteristics to it. Right? So sound is, kind of what we perceive. It's what you guys are all hearing right now from the sound of my voice, right? So sound has two main characteristics in general, right? So there is the loudness or the volume of the sound, and there is the pitch, okay? Right? So both of those characteristics contribute to what we interpret as sound. Now, of course, sound is a lot more complex than this. Acoustics are a lot more complex, but at a baseline level, these are the two main characteristics, right? So the reason I bring these up is to kind of relate them to what we're going to discuss in terms of Fourier. Right? Now, Fourier series is all about periodic functions. Right? So I'm sure you guys have seen periodic functions before. Periodic functions are simply functions that repeat themselves, right? So they have basically the same pattern that goes over and over and over, right? Just like sound, we can characterize periodic functions by their two main characteristics. Right? So periodic functions are characterized by its amplitude, as well as its frequency. Right? Right. Which, you can tell just by the way I've kind of, listed these two things kind of side by side. Amplitude is essentially the same thing as volume, right? And the frequency determines the pitch of the sound, okay? Right. And so for any given periodic function, right? So let me go ahead and draw one out here. So let's say we have a simple sine wave here. Right? Remember, the amplitude is the vertical distance from the peak down to the average, right? So this distance right here would be the amplitude. And the frequency tells us, how quickly our pattern will repeat itself, right? So, frequency is a bit interesting. So, this distance right here, from the origin up until the point where that pattern repeats, we call this the period of the function, right? That's the amount of time it typically takes for a signal to repeat itself. But the frequency is 1 divided by the period. Right? And the way that we interpret frequency is that we can say that the wave or the function repeats itself every such and such seconds. Okay? Okay. And we can represent these two ideas mathematically as well for a typical periodic function, right? Now, when you say periodic function, I think the first thing people think of are just sines and cosines. And so those are kind of the quintessential periodic function, right? But periodic functions can be anything, right? So as long as the function repeats itself, it's considered periodic. It's most concise to kind of talk about sines and cosines. And this idea of amplitude and frequency is encoded directly in the way that we express our sine and cosine function, right? So typically, when you have a sine or cosine functions, it looks something like this. Right, so usually there's some number, some coefficient out in front of the sine or cosine, and then inside the argument of the sine or cosine, we have some coefficient multiplied by time, right? Now, of course, you know these quantities. So this A naught here, this is, of course, the amplitude. And this omega is our frequency. Right. So two very simple concepts that you've no doubt seen in some way or form in your previous classes. Probably you've seen this in your physics classes as well. But these are going to be kind of core to our understanding of Fourier. Okay. Okay. All right. So that's just kind of a review and kind of an overview of what we talked about last time. Any questions about this? Okay. All right. So then now that we kind of have the baseline kind of established here in terms of periodic functions, let's talk about exactly what the Fourier series is. I think when most people hear the word series in a mathematical context, it kind of gives a little bit of a little bit of anxiety. Because I think probably everyone's familiar with the Taylor series and probably the first series that you're accustomed to. I want to say that Fourier series is not as confusing, but I've also been teaching this for 7 years now, and so I've seen it probably more than you guys have. So okay, so what's the idea with the Fourier series? So Fourier series is a method for what we call functional representation. in particular, Fourier series gives us a way to give us basically an alternative representation for any periodic functions. So it's basically a way to say that you have a periodic function. We want to represent it in another way. The Fourier series gives us a way to do it. Okay. Okay, so in particular, right, the Fourier series, what it basically says is that we can take any periodic function, so basically any function that repeats itself, no matter if it's a sine or cosine function, or no matter if it's any kind of weird function. And what Fourier says is that we can take any periodic function and perfectly represent that as an infinite summation of sines and cosines. Okay, so let me kind of show you what that means here. Okay, we can take any function f of t. Okay. So this f of t here is basically any periodic function. The only requirement for that periodic function is that it is periodic. So there is kind of a fixed frequency. There is a pattern to how it repeats. Okay. Right. And what we say is this is equal to the summation from n is equal to 0 to infinity, okay, of an cosine of nt plus bn sine of nt. So this is saying that any, and I mean any, any periodic function can be represented by an infinite sum of sine cosine. Okay. I remember when I first learned about this, it was actually in a physics course. So I was taking a basically physics 2, which is electricity and magnetism. And my physics teacher said this like it was the most amazing thing in the world. And I remember thinking back at the time, I was like, that I don't understand why this is amazing. So I'm going to hopefully kind of explain what this means, but it's there's a lot of really interesting consequences to this, and it is actually really cool once you kind of really start to understand. Okay. Okay. All right. So what do I mean by this? And so when I say any periodic function, I mean anything. And so even functions that are defined piecewise, right? And so for example, right? So functions that you would look at it and you think, that doesn't look like a sine or cosine at all, right? So let's say that we have a typical, let's look at a square wave. And so a square wave might look like the following. Okay. Right. So this is a function here that is, it's periodic. We can see that it's repeating itself, but there are kind of sharp changes, right? And so it basically looks like our step function here, but we are kind of, changing magnitudes or changing the polarity, every so often. Okay. Now, a function like this, is, like we talked about before, it doesn't really have a strict mathematical description, at least not as a continuous function. So the only way to kind of represent this exactly in this form is to use basically a piecewise function. Okay. right? So typically we say that, f of t is equal to maybe positive k from 0 is less than t is less than a, and then maybe negative k from a is less than t is less than b, right? Right, that's typically how we would represent it by some kind of discontinuous function. Okay. All right, but with the Fourier series, what we're saying is that even this kind of weird function here, this weird discontinuous piecewise function, we could actually represent that as a summation of sines and cosines, right? Where sines and cosines, unlike this function, are continuous functions, right? And so there kind of seems to be a little bit of a disconnect. Right. But this is actually true. So, any periodic function, no matter how discontinuous, you can come up with an exact representation using sines and cosine functions, as long as you sum up enough. Okay. Okay. So what we're going to be doing is basically we're going to be learning how to take any periodic function and determine its Fourier series representation. Okay. And by determine its Fourier series representation, what that means is that we're going to come up with expressions for the coefficients here. Okay. So an and bn here are what we call the coefficients of the expansion. Okay. So the idea is that if you can determine the coefficients, you determine everything about the expansion. Okay. All right, so that's where we're going to go. So we have basically our Fourier series expansion always has that expression there. We want to determine the coefficients, and we're going to learn how to do that for given different situations. Okay. All right, any questions on this so far? Okay. All right, so let's go ahead and let's learn how to compute the coefficients. Okay. All right, so the coefficients, we're not going to derive them. I'm just going to give you the expressions for them, are given by the following formulas here. Okay. Okay. So the formula for an is we're going to take 1 divided by pi, and then we're going to multiply by the integral from minus pi to pi of your periodic function f of t cosine of nt dt. Okay. Right. And then our bn is equal to 1 divided by pi integral from minus pi to pi of f of t sine of nt dt. Okay. All right, so pretty straightforward formulas here. So now the integral might be a little bit annoying to do just because we have sine and cosine. So you may have to do integration by parts or integration by table. But it is a fairly straightforward expression to do. Okay. And then there's one more, there's actually one more equation to know. Okay. So if you notice in our Fourier series here, our summation actually starts at n is equal to 0, right? Right. And so when you plug in n is equal to 0, right? N is equal to 0 is kind of an interesting spot where you plug in 0, you get cosine 0. Cosine of 0 is actually 1, and sine of 0 is actually 0. Right? So we actually, a lot of times we treat the A0 term separately. Okay. So A0 kind of has its own special expression here that does not involve the cosine. Right? So A0 here is computed by taking 1 divided by 2 pi integral from minus pi to pi of just f of t dt. Exactly. Exactly. Yeah. So technically A0 you can get from AN as well. You just plug in N is equal to 0. It's just that traditionally we kind of, keep it outside on cell. Yep. All right. And so one thing to note about these formulas here is that this will only work if our periodic function has a period of 2 pi. Okay. Which is very limiting, I know, but later on we're going to see how these concepts expand to an arbitrary period. But for now, we're going to stick with 2 pi because that's a good place to start. Okay. Okay, so let's go ahead and apply this to an example here. It will actually be the exact same, well, almost the exact same square wave that we looked at before. Okay, so let's consider the following periodic rectangular wave. All right, so we have f of t is equal to, we have minus k for values of minus pi, which is less than t, which is less than 0, and then positive k for 0 is less than t is less than pi. Okay. And then the assumption is that after pi, then the pattern will repeat. Okay, so if you want to draw this function out, it looks like the following. Okay. So horizontal axis here is t. Our vertical axis here is f of t, right? So from minus pi to 0, right, our function has a value of minus k, so it looks like this. Okay, where k here is just some number here, and then from 0 to pi, our function here has a value of positive k. So our pattern looks like this. And then after this, the assumption is that it's going to repeat, right? And so outside of this, let me go ahead and use another color, right? It's going to repeat. So it's going to be down to negative pi, and then positive pi, or negative k, negative k, and so on and so forth. Okay, but I highlighted in red there just the first period that we. Okay. And so what we want to do in this case is that we want to compute the Fourier series coefficients for this function. All right, good. All right, so all we're going to do here is we're going to take this periodic function, we're going to integrate it over one period, so from minus pi to pi, and then that's going to give us our, our coefficients. Okay, so let's start. Let's actually start with A0. A0 is kind of the simplest one. Okay. All right, so let's compute A0. So A0 in this case is going to be integral from minus pi to pi of f of t dt. Oh, forgot the 1 over 2 pi out in front. Okay. Right, so all we're going to do is we're just going to plug in f of t. Okay. Now, in this case, our f of t is a piecewise function, right? So it has a different definition from minus pi to 0, and another definition from 0 to pi. And so let's split up that integral, just like we've been doing. And so this is going to be 1 over 2 pi multiplied by integral from minus pi to 0. Okay. So from minus pi to 0, our function here has a value of minus k dt plus integral from 0 to pi And so from 0 to pi, our function has a value of positive k. Right? And so we're just integrating over a constant here. And so there's not much to do. Right? So let's go ahead and do that. So we have 1 over 2 pi multiplied by integral from minus pi to 0. That is minus k times t, evaluated from minus pi to 0, plus k times t, and evaluated from 0 to pi. Okay, so let's go ahead and evaluate this. So we have is equal to 1 over 2 pi minus k multiplied by 1, 0 minus negative pi plus k times pi minus 0. Okay. All right, and so we just evaluate this. The first term is a little bit tricky because we have 3 negative signs there. We can see negative k times negative pi, that is a negative pi, plus k times pi, and so the interior of that will cancel out. And so a0 here will be 0. Fourier can be very satisfying because there are a lot of situations where your coefficients are just going to end up 0. We'll talk about those kind of in more detail later. So this right here is a very classical case of a situation where a0 and actually an are going to be 0 as well. And so, we'll learn how to identify that. But in this case, a0 is equal to 0. Any questions? Yes.
Just out of curiosity, so just before it involved, quick question. A0, if it has a value, that means it's starting somewhere along the line. It's just
Yes.
0.
It is. Yes.
What does that look like in real life? Does it sound like just a sudden sound or some vibration? No.
So a0 actually has a very special interpretation. And so actually, if you look at this formula here, right? This is a point we'll get into later, but I think now is a good time then to talk about it. So we're basically taking the integral of that function across one period, and we're dividing by 2 pi, right? So 2 pi being the period, right? So that's a formula you've seen before. You may not have seen it for a while, but this is our mean value formula. And so a0 is actually nothing more than just the mean value of our periodic function. And so if you have in this case, our mean value is 0, right? Because if you look at our function here, right, we kind of spend equal amounts of time at minus k and equal amount of time at positive k. And so, the mean value for that is going to be 0. And so it makes sense that a0 is 0. But you're also going to have some periodic functions where maybe they're offset from the t-axis. And so there's kind of a non-zero mean. And so that's always reflected in. Yeah. Any other questions on this part here? Okay. All right. So let's go ahead and compute an. So this one's a little bit more complicated. So an, the formula for that is 1 divided by pi, integral from minus pi to pi, f of t, cosine of nt dt. All right, so just like we did with a0, let's go ahead and plug in f of t. We once again have to split our integral into 2, just because we have a discontinuous function. And so this is 1 divided by pi, multiplied by integral from minus pi to 0 of minus k cosine of nt dt, plus integral from 0 to pi of positive k cosine of nt dt. Okay. Okay, so we have 2 integrals to do, but they're essentially the same. It's just a constant multiplied by cosine. So let's just integrate cosine nt. Okay. Just to kind of simplify things a little bit, I am going to take this k just because it's a common term between both of our expressions here, and just pull it out of the expressions here. Right? Right, so we're gonna have k over pi multiplied by, we have integral of cosine nt, so that is a sine of nt divided by n. Okay, so that's gonna be minus sine of nt divided by n. Okay, that minus sign there comes from the minus k. It doesn't come from the integral. Plus sine of nt divided by n. Okay. First sign here, this is evaluated from minus pi to 0. Second one is going to be evaluated from 0 to pi. Okay. All right. So let's go ahead and plug in our integration bounds here. So k over pi out in front. Okay. So first, for the first integral here, we have a minus sine of 0. Right. Remember, we're plugging in for t. We're not plugging in for n. Okay? So you want to be careful about that. Divided by n. Plus sine of minus n pi divided by n plus sine of n pi divided by n minus sine of 0 divided by n. So all I did there was just plug in our integration bounds for t. Okay, so let's look at some of these expressions here, right? So a couple of these we can kind of cancel out right away because we have sine of 0, right? So what do we know sine of 0? Sine of 0 is 0, right? So the first term and the fourth term are both going to be equal to 0. We can just nail those from the right away. Okay, now the middle two terms, right? So let's remember here what n represents. So the n, right? You kind of scroll all the way back up here, right? This n here is not just any number here. That n there is our summation index, right? So n is actually very special in that it's not just an arbitrary number. It is going to be a whole number, right? So it's always going to be an integer. Okay. And so that actually carries some very important consequences, right? So since we know n is going to be a whole number, it's either going to be 1, 2, well, I guess technically 0 as well. So 0, 1, 2, 3, 4, 5, 6, right? It's always going to be a whole number, right? And so if we look at these two expressions here, right? We have sine of an integer multiplied by pi, right? So that argument in there is always going to be some multiple of pi, right? So we're going to have sine of minus pi, sine of minus 2 pi, sine of minus 3 pi, and so on and so forth, right? So for basically all values of n. So technically, you know, we're taking infinite summation. So n is going to take every single integer value from 1 all the way up into infinity. Okay. But what do we see from all of these sine terms, right? So sine of minus pi, right? Sine of minus pi is equal to basically sine of 180 degrees. That is 0. Sine of minus 2 pi. 2 pi is the same as 360 degrees. Sine of 2 pi is 0. Sine of minus 3 pi. So minus 3 pi, that is basically 1.5 full rotation. So that's what? That's 540 degrees. That is also 0 because, you know, you rotate from the positive x-axis, you rotate 100, 540 degrees, you end up back on the x-axis. Also 0. Okay. So based on kind of what we know from trig, and based on the fact that n here is an integer, we can say that those terms, sine of n pi, are going to be 0 for all values of n. Right? And so if those are equal to 0, right? We have nothing left to have here, and so that means that an is equal to 0 for all values of n. So it's typically going to be the case where if you solve for a0 and it's 0, an is typically also going to be 0. That's just kind of the nature. Although not always. There are some cases where you have a non-zero mean value or a 0 mean value, but a non-zero mean. Okay? But in this case, it just happens that both of them are. Okay. So kind of a small note. I don't have this in the notes, right? But this fact right here is something of a pattern that you're going to see quite a bit in all of Fourier, right? So it's important to kind of know what this kind of represents here. Because you're going to see sine of n pi a lot. Okay? All right. Any questions on this part here? Okay. All right. So that's an. So let's finish up our problem here and let's compute bn. So bn better be something because a0 and a0 and an are both 0. So that means bn has to be something. Otherwise, we don't have an expansion here. Okay. So bn, we have 1 over pi integral from minus pi to pi f of t sine of nt dt. Okay, so I'm going to go a little bit faster here just because, we've seen this. This is the third time we've seen this. And so, we're going to go ahead and split up this integral here. Okay. Integral from minus pi to 0 of minus k sine of nt dt plus integral from 0 to pi of k sine of nt dt. All right, so let's go ahead and do this integral. So instead of cosine, we're now integrating sine of nt. Okay. Now, just be aware when you integrate sine, there is that negative that comes out because the derivative cosine is minus sine. So just make sure you get that. So just like we did with an, I'm going to take the k's. I'm going to pull it out of the integral here. So we have k over pi. Okay. And so integral of minus sine nt from minus pi to 0, that's going to be a positive cosine of nt divided by n, evaluated from minus pi to 0, minus cosine of nt divided by n, evaluated from 0 to pi. All right, so let's go ahead and plug in our integration bounds just like we did for an above. Okay. All right, so we do that. We get k over pi is still out in front. And so we're going to have cosine of 0 divided by n minus cosine of minus n pi divided by n minus cosine of n pi divided by n plus cosine of 0 divided by n. Okay. Bless you. All right, so let's go ahead and simplify this, right? And so first thing, right off the bat, we see we have cosine 0. So cosine of 0 is 1, right? So that's great, right? And so we get something non-zero for once, which is really good. Okay. All right. And then we have cosine of n pi and cosine of minus n pi. Okay. Okay, so there's a couple of things going on with this, and so let's kind of take it step by step. Okay. So first, let's look at cosine of minus n pi, or minus pi n, just because my brain wrote pi. Okay. Okay. So we can actually simplify this because cosine is actually very notorious for being what's called an even function. So the fact that cosine is an even function, right? What that means is that our cosine function here is symmetric across the vertical y-axis. And so if you plot cosine, right? So cosine notoriously starts at 1 and then it goes down like that, right? Right. If you draw a line of symmetry, right? And so if you draw kind of a symmetry line on the vertical axis, you can see that everything on the left has a corresponding mirrored entry on the right, okay? And so the consequence of this is that we can basically take any negative in the argument of the cosine and turn it positive, right? So cosine of minus pi n is actually equal to cosine of positive pi, right? Right, because any term here, so this right here will be cosine of positive t, right? It has a mirror image on the other side, so this is cosine of minus t, right? So for any even function, you can always kind of make this relationship here, where you basically you almost kind of cancel out that negative. Okay, so that's really nice because what that allows us to do is that allows us to combine both of these terms because they are the same, right? So we have minus cosine of minus n pi, that's the same as cosine of n pi, and so that allows us to combine it with the other. Okay. Okay, so we perform that simplification, we combine that together with the 1. I'm going to take that 1 over n and just factor it out. Okay. And so we have k divided by n pi multiplied by positive 1 minus cosine of n pi. Oh, there's 2's here. Yes, thank you. So 2 minus 2 cosine n pi. Okay, so that's kind of the basics of how you compute your Fourier series coefficient, right? So you have basically your 3 integrals to compute, and you just kind of work your way through. Okay, eventually, you should get at least one of the coefficients, whether it be an, bn. Usually, one of those two will be some non-zero expression. All right, any questions on how we got to this point here? Yes.
Can you explain how we got 2 cosine and pi?
Yeah. So we had two terms after our integral here. We had cosine of minus n pi and cosine of positive n pi. And so we made use of the fact that cosine was an even function. And so we basically said that this cosine of minus n pi here is equal to cosine of n pi. Yeah. And so we have two minus cosine of n pi, so we just combined it. Yeah.
Thank you.
Mm-hmm. Okay, good. All right, so there's actually one more thing we can do to simplify this, and that has to do with this cosine of n pi here. Okay, so just like before, right? So if we look back at our an expression, we saw that sine of n pi kind of has a very specific value of 0, right? So no matter what value of n that we choose, since n is an integer, sine of n pi is always going to be 0. Okay. Cosine n pi is something similar, although it's not 0. Okay. So let's plug in different values of n, and let's see what we obtain from this cosine n pi here. Okay. So we plug in n is equal to 1, we get cosine pi, right? Cosine pi gives us -1. Let's plug in n is equal to 2. N is equal to 2 gives us cosine 2 pi, which gives us +1. Okay. All right, we plug in n is equal to 3. We get cosine 3 pi. We're once again back at -1. Okay. Cosine of 4 pi, that's 2 full rotations around the origin. That gives us +1. Okay. So we can kind of sum this up, right? So you can kind of, I'm not going to write more than 4, but trust me when I say this pattern repeats, right? Basically, whenever n is an odd number, right, we get -1. Whenever n is an even number, we get positive, right? So another way that we can express this that I think is a little bit more clear is we can say that cosine of n pi is equal to -1 raised to the n power, okay? Right, because that gives us the exact same result, right? So -1 raised to the n power, you plug in n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and it follows that same pattern, okay? So I like this, so I like putting -1 to the n power because I think it's a little bit more descriptive, but technically this expression right here is correct. You can leave it as cosine n pi, as long as you know what you're doing when you're plugging in, but my own personal preference is to plug in for -1 to the n. Okay? Okay, and so that gives us our simplest expression for Bn, right? And so that is, I'm going to go ahead and factor out the 2 as well, right? So on the numerator here, we have 2k divided by n pi multiplied by 1 minus -1 raised to the n. Okay, good. All right, so once you kind of have an expression like this, you can start to plug in different values of n, okay? And so remember, these are coefficients in an expansion. And so while this formula here gives you the general expression for what the formula for what the coefficients are, it's always good to kind of plug these in so that you can kind of see what the expansion actually looks like. So let's plug in, let's plug in 4 values of n. Okay, so let's compute the first 4 coefficients. Okay, so let's start at, well, we know B0 is equal to 0, so let's start with n is equal to 1. Okay, so we get n is equal to 1. What we get is B1 is equal to 2k divided by pi multiplied by 1 minus -1. And so that's 4k divided by pi. All right, next we have n is equal to 2. So we have B2 is equal to 2k divided by pi, or 2k divided by 2 pi, excuse me. I always forget the n out in front there. 1 minus -1 squared, which is 1. Okay. Right, and so we get 1 minus 1 inside their parentheses, and so that, of course, is equal to 0. N is equal to 3. Let's go ahead and plug that in. We get B3 is equal to 2k divided by 3 pi multiplied by 1 minus -1. Okay. Because n is an odd number, so our cosine of n pi gives us a -1. Okay. So then this gives us 4k divided by 3 pi. Okay. And then n is equal to 4. We get B4 is equal to 2k divided by 4 pi multiplied by 1 minus 1. Okay. Which, of course, again, is equal to 0. Okay. So now that we know the first four coefficients, let's go ahead and write this into our Fourier series expansion. Okay, so let me give you the Fourier series expansion again here. And let me give you kind of the modified form with A0, right? Right. So with the A0 term kind of outside, we get f of t is equal to A0 plus summation. Now our summation is starting at n is equal to 1 of an cosine of n pi, of nt, excuse me, plus bn sine of nt. Okay, so all we're going to do is we're going to plug in our results for A0, AN, and BN into this expansion. Okay. Now for this problem, we found that A0 and AN are 0. Okay? So that means both of those are going to cancel out. So all we have left here is the summation of Bn. And in fact, a lot of the Bn's are also equal to 0 as well. So B2 and B4 equal to 0. Okay. So writing in the first two non-zero terms here, we have B1 sine of t, right? So that's going to be t n is equal to 1 plus B3 sine of 3t. Okay. Notice how each coefficient, the frequency of the sinusoid also changes as well. Okay. Okay, so let's go ahead and plug in what we obtained from B1 and B3. Right, so we have f of t is equal to B1 is equal to 4k over pi sine of t plus B3 was 4k over 3 pi sine of 3t. Okay. And remember, this summation here is an infinite summation. So technically, there are a lot more terms that can happen. Okay, so almost always, when you have your Fourier series expansion, you're going to have a dot 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 at the end, just because the expansion continues. But at least we can write out at least the first couple non-zero terms. Okay, and so that's what I would kind of characterize to be kind of a full Fourier series problem, right? So you take your function, you compute its coefficients, and then you plug them into the expression to get something. All right. Any questions on this so far?
And then do you want us to write in a summation in format as well, or?
No, usually this form is usually good because I want to see the actual kind of plugged in for the coefficients. Okay. It gets a little bit messy when you plug in kind of so this one's actually pretty clean. So this Bn is not too scary, but as our functions get more complicated, our coefficients are going to have more kind of scary expressions. And so yeah, I find it's just a little bit cleaner to kind of just plug it in and just give me something. Yeah. Okay. All right. So before we move on, right, and so the next step is of course, how do we compute Fourier series expansions for arbitrary periods? So let's take a look and let's take a minute to kind of look at this result here and kind of make some comments. Okay, so first comment that that's kind of obvious is that this is an infinite summation. So technically, we can compute an infinite number of these terms here, right? And so technically, if you wanted to make the true Fourier series expansion, you have to keep computing n terms all the way up into infinity. Okay. Now, of course, that's not practical, right? So, it's no one has the time to compute an infinite number of terms. That's literally impossible because it's infinity, right? And so, practically speaking, whenever you make a Fourier series expansion, you have to cut it off at some point, right? So you have to stop computing coefficients. Okay. Right? And so in this particular case, we stop computing coefficients at n is equal to 4, right? But in reality, you can kind of stop whenever you. Okay. All right. So in most cases where you see Fourier, you see this a lot in signal processing. Usually a fairly good cutoff value is 10, right? So you compute the first 10 values. Okay. Because beyond that, you kind of get diminishing returns. Okay. So this process or when you cut off the expansion at some point, we call this truncation. And so the way you typically say is that we truncate the expansion at n is equal to 4, or we truncate the expression at n is equal to 10, right? So basically anything that's higher than your truncation point, so n is equal to 5, 6, 7, we basically just throw those terms. Okay. So we're literally kind of throwing away all those terms, past that truncation. Okay. Now you may see that and you think, hey, our summation goes to infinity. And so, we truncate at, even at a high number, right? So let's say we truncate at n is equal to 20, right? You're technically still throwing away an infinite number of terms. And so aren't we losing a lot of information? Aren't we losing a lot? Well, most times you're not actually losing that much information. Okay. Because I want you to look at something, right? And so, unfortunately, I can only show you it for this example, but actually, most periodic functions are the same, right? So I want you to look at, one specific feature of our expression for Bn, right? It's the fact here that n is in the denominator here, okay? And so, exactly, right. So as n gets higher, that means the magnitude of our coefficient is actually going to go down. Okay, and that's generally true for most periodic functions. Okay, so generally magnitude right? And so when you're truncating an expression, like it is true, you are throwing away a lot of coefficients, but generally you're throwing away coefficients that have a very small, very negligible value or magnitude. Okay, so you're usually not losing all that much information. But with that said, the more terms that you preserve, right, the more terms that you actually compute, the more accurate your expansion is going to be. Okay? And so you kind of have very interesting kind of cost benefit analysis that kind of occurs here, right? And so in general, you want your expansion to be fairly accurate, right? But it becomes a question of, how hard do you want to work for that accuracy, right? Because if you want true accuracy, right, then you do an infinite summation, but you can't do an infinite summation in most practical situations. So you have to cut it off at some point. But then the question is, where do you cut it off to preserve most of your accuracy that you have? Okay. And of course, there's no general answer to that, and so that is kind of application specific, right? But it is something that you have to think about if you are going to be doing work with Fourier. Is how much accuracy do you want, and how many terms do you want to retain? Okay. All right. Any questions on this? Okay. All right. So I think we'll save the general Fourier expansion for next time, just so we only have 15 more minutes. But I do want to cover kind of one important aspect of Fourier, which is the concept of orthogonality. Okay, so orthogonality is actually a very big topic in just applied math in general. There's applications to all different aspects of math. So we're only seeing a very small slice of it, but Fourier series is actually one of the best examples of orthogonality. Okay, so what orthogonality basically means is that when you have a system here, right, or when you have a mathematical technique that relies on different basis functions or basis vectors, the one important aspect is that all of your basis functions must be orthogonal to each other. That's how the expansion, that's how the breakdown works. So Fourier series, okay, we can say relies on the fact that its basis functions being sine and cosine, right? Its basis functions are orthogonal to each other. Right? So I gave you kind of a very roundabout definition, but let's actually define what orthogonal means. Okay. So orthogonal basically means when you take kind of a product, what we say kind of an inner product of two basis functions, you get zero unless the two basis functions are exactly the same. Okay, so for example, let's say we take the inner product between two cosine functions, right? Now, what is the inner product, right? Because that's kind of an interesting term that I use there. Now, an inner product is kind of a way to basically interact two different basis functions, and it depends on the space that you're working with, okay? Now, for Fourier series, an inner product means integrating the product of our two basis functions across a period. Okay. Okay, so for example, right, taking the inner product of two cosine functions, right? So let's say we take integral from minus pi to pi of cosine of t dt, okay? Right, so this would be the inner product between two cosine functions where you multiply them together and we integrate them across a period, okay? Since these are two identical, basis functions, what you're going to get here is 1. Okay. right? So I'm not going to actually do that integral because you've probably seen that before, cosine squared, but trust me when I say that it's okay. Meanwhile, if you take the product of two different basis functions, minus pi to pi, okay, so we take cosine of t, sine of t, right, dt, this gives us 0. Okay, because these are two different basis functions. Okay, you multiply them together, you integrate, you get 0. Now, this orthogonality also applies to different multiples of different frequencies of our basis functions, right? So cosine t are the same, but cosine of t and cosine of 2t are not the same, right? So if you take the integral from minus pi to pi of cosine of nt multiplied by cosine of mt, where mt or m is different than n, dt, okay? Right, so technically these are two different basis functions as long as n does not equal to m, right? This is also going to get you 0. Right, so that's what it means to be orthogonal, right? And so basically, when you take the inner product of any two basis functions in your expansion, you get 0. Okay. Now, for sine to cosines and Fourier, there's lots of different combinations, but I think kind of a very easy kind of example of orthogonality can be given by how we understand our Cartesian coordinates. It's a little bit of a shift, but I think it kind of helps to illustrate this idea of orthogonality. Okay, so when we're talking about Cartesian coordinates, right? We have basically two basis functions, or I guess to be more accurate, say they're basis vectors. Okay. Okay. We have the I hat vector, which is simply 1, 0, and j hat, which is 0, 1. Right? So I hat is a unit vector that points in the positive x direction. J hat is a unit vector that points in the positive y direction, right? These two form the basis for a location in Cartesian space. Okay. Okay. Because what can we do with this I hat and j hat? We can basically use these to specify the Cartesian coordinates of any given point. Right? Exactly. Right. Right. Since I hat and j hat, they span the entirety of that R2, 2D space. Right. So just a very quick example, right? So let's say that we have the point 3, 6, right? We can express this as 3 times I hat plus 6 times j hat, right? So you might have seen that notation in your math classes before. You're thinking, what is that? That's weird. Why don't you just use parentheses? We're essentially using the basis. Okay. Now, the inner product for Cartesian space is actually just the dot product, right? Everything kind of comes back to dot product. And so if you take the dot product between I hat and j hat, you'll see that you get 0 because they are different basis vectors, right? So we take I hat dot product with j hat, right? Right. You don't even have to we don't even have to kind of write it out. We can see that it's 1 times 0 times plus 0 times 1, which is equal to 0. Okay? Meanwhile, if you take the dot product between two of the same, right? So I hat dot I hat, this gets 1. J hat dot j hat is equal to 1. Okay, so that's kind of the idea of orthogonality, right? So for Fourier, obviously it's more complicated than Cartesian just because we have so many different bases and it depends on kind of the value of n in our expansion, right? But the reason that we can do a Fourier series expansion is the fact that our sine and cosines are orthogonal given their inner product, okay? And in fact, you can take this even a step further, right? So I'm not going to do this here just because, we're just about out of time. But what you can do is you can take, this orthogonality and you can use this to derive the expressions that we have for the coefficients. So, these, where are they? These formulas here. So these formulas were born from the fact that, these sines and cosines are orthogonal to each other. Okay, any questions on this? Okay, all right. So I think we'll pause here for today. I know it's a little bit early, but it's not really worth starting the next thing. So when we come back on Thursday, we'll talk about Fourier series expansions for cases when our period is arbitrary. So the next what we cover Thursday, that's what you're generally going to be using for the most cases, because most periodic functions don't have a period of 2 pi, right? And then we'll do an example for that, and then we'll cover just some extra topics with Fourier to help you out with. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day. If you haven't picked up your exams, today is the last day I'm bringing them. So please come up and take your exam. If not, I'll see you guys on Thursday. You too, Anthony. Thanks, Pablo. Yeah. You too.
Thank you.
Mhm.